Hello, this is an introductory lecture in the module Fourier analysis. At the time of recording, I am the module leader. My name is Alexander Pushnitsky. So let me start by an example. Let's consider the following problem. Suppose we have this function, let's call it a square wave, and let's try to approximate it by taking sums of simple sinusoidal curves. So this is the graph of sine x, this is the graph of sine 3x, and so on. So let's try to approximate the square wave by taking sums of sine curves with increasing frequencies. So at a first glance, it seems an impossible problem because the square wave has these corners everywhere, and so we cannot approximate it with a smooth sine curves, it would seem. But if we try, let's try taking the sum sine x plus 1/3 sine 3x. So I take this curve multiplied by 1/3 and add to this graph. And it looks like what we've got is beginning to resemble a little bit the square wave. If we take more terms, for example, if we take 10 terms of a similar nature, we take sine x plus 1/3 sine 3x plus 1/5 sine 5x and so on up to 19, we take some odd numbers, then what we get is really quite a good approximation to this square wave. So this example illustrates the general thrust of Fourier analysis. So let's now consider a more general problem. Suppose we have a function f, which is 2 pi periodic on R, which means this. Can we represent it as a sum of sines and cosines with some coefficients an and bn? So the frequencies are all multiples of 1. So all these terms here are 2 pi periodic, and this series may be a finite sum or maybe an infinite series. So this was the question that was formulated in the late 1700s, early 1800s years, and an equivalent formulation for this problem is the following one. If we rewrite sines and cosines in terms of complex exponentials by using Euler's formula, then the question takes an algebraically simpler form. Can we represent any 2 pi periodic function f in terms of this infinite series, where the frequencies n range from -infinity to infinity? So the answer that was given by Fourier is yes, we can. Any reasonable 2 pi periodic function can be represented in such forms. And today, this infinite series is called the Fourier series, and we say that f is expanded in Fourier series. The coefficients Cn are now called Fourier coefficients, and the surprising thing is that there is an explicit simple formula for these coefficients. You just have to take this f and integrate over the period with the factor e to minus inx, which is the complex conjugate of this term that we see here, of this exponential. So roughly 1/2 of this module is about Fourier series, about in what sense do they converge, when can we expect them to converge, and some applications of those. The other half of the module is about what is called Fourier integral, which is, roughly speaking, a continuous version of this series. We replace series by integral, and so now we expand a function f, which is not necessarily 2 pi periodic, it's just a function on the real line. We expand it across these oscillating exponentials, but the frequencies are now not discrete, not 1, 2, 3, and so on, but they are labeled by continual variable xi. So this is the outline of the contents of the course. There are many applications of Fourier analysis in signal processing, image processing, crystallography, and so on. And of course, many applications in mathematics as well. So the recommended textbook is Fourier analysis by Stein and Shakarchi. This is a recording of lecture notes of lectures given in Princeton. Finally, a few words about organization. Level 6 and Level 7 module versions of the module have the same lectures, but the exam paper is slightly different. Assessment is by 2-hour written exam paper. Tutorials supplement lectures, and homework is given at the tutorials for your practice, but it does not contribute to the assessment. Thank you for listening.